Hello, Internet. So in this particular video, I will be building a model using TensorFlow Keras, and it will be a custom model. So for example, we will be considering this particular dataset, Intel image classification. It is available on Kaggle. I'll also include the link in the notebook itself. And let me comment it out. Yeah. And I'll be posting the link of the GitHub repository where this particular notebook will be kept. And this particular data set consists of 6 classes: forest, glacier, mountain, sea, street, and buildings. So let's begin. Let me connect this Colab notebook with my Google Drive, because I have kept this particular zip file on my Google Drive. Let me just unzip it. Unzip drive, my drive, dataset, and Intel _img.zip. Let me extract it. Okay, so the name, let me just check. It should be Intel IMG. Just check whether the drive is connected or not. Then data set. Okay, so this should be data sets. Okay. Now it should extract. By the time it extracts, let me tell how we are going to proceed with the execution. Execution steps. I will try to keep it as simple as possible. First, we will import necessary libraries. Then load the data and create data loaders. Then third, we will build model, and fourth, we will train and evaluate the model. Let me just highlight it. Okay, execution steps. So step 1, import libraries. So import OS, then import NumPy as NP, then from PIL, which is the pillow library. I will be importing image. Pillow library will help us read the image file. And NumPy will help us convert the image into an array, 3-dimensional array, because the image files will be colored. So the third dimension, it will be a 3-channel image. So then from TensorFlow Keras, we will be importing preprocessing.image import image data generator. So this will help us read the image and convert them to features and target. Then from layers, let us import convolution 2D, then average pool 2D, then batch normalization, then dropout. Dropout will help us reduce overfitting of the model. Then flatten, because before passing the parameters, that is the passing the output of convolution layer outside to the linear layer, that is the fully connected layer, we need to flatten them out. and then dense. Dense is the linear. Then from TensorFlow Keras dot models, I will be importing sequential, and then we will import other libraries as and when we will need them. Two libraries that I can recall is import matplotlib.pyplot as plt, and from random import randint. I'll explain why I have imported them when we will use them. So this is step 1 complete. Then proceeding to step 2, which is load the data. Step 2, load data. This, let me put it in this text block. Okay. So let me create image generator and image data generator, and rescale. I will set it to 1 divided by 255 because pixel intensities range from 0 to 255. So we are basically normalizing it. So the values, minimum value will be 0 and maximum value will be 1. So the values will be between 0 and 1. Let me execute it. And then train loader will be this img gen dot flow from directory, and here the parameters that we will be using is, first one is directory, then second one is target size, I don't know why it is not copying it. Target size. Third one is batch size, then the remaining shuffle and all seed. So it matches seed. Let us keep it 42. So if you want to train at your end and want to compare it with mine, then you can use seed as 42. Then directory, let me pass the directory. So this is the training folder. So sec train slash sec train, and in this you have this 6 subfolders containing the images. So seg train slash seg train. Target size, we will resize the image to, let's say, 128 by 128. Then batch size, let us keep it as 50. And then this is done. Then similarly, we will build for test loader. So instead of seg train, it is seg test. The remaining all parameters, let's keep it as it is. If you want to see the class indices, you can type class indices. So you will see the mapping. Buildings are mapped 0, forest 1, glacier 2, mountain 3, sea 4, street 5. I'll create a dictionary IDX index to classes, wherein the keys will be the numbers 0 to 5 and values will be buildings, forest, glacier, mountain, sea, and street. That is basically just interchanging the keys and values of this particular dictionary. So let me create a dictionary comprehension val key for key val in. I'll wrap it in dictionary, and in dictionary I'll pass this, and then dot items. And for our understanding purpose, I'll just show this. There you go. Then step 2 is complete. Now moving on to step 3. Step 3, build model. So let me define the model sequential, and then model dot add. So first will be the convolution layer, conv 2D. Filters will be 32. Then kernel size will be 3 by 3. stride padding, that will remain the same. This next that we want is this activation function. So where did it go? Activation equal to, let us use ReLU because it is a hidden there, and input shape will be 128 by 128, and since ours is a color image, it will be a 3-channel image. Then after convolution, we will use average pool 2D and pool size. At the beginning, let's keep it 3 by 3. Then model.add, I will apply batch normalization to normalize the output, and then model.add dropout, and we will pass in dropout at 0.3, so it kills off 30% of the neurons. So dropout helps us prevent overfitting of the model. So this is convolution 1. Similarly, let us add one more convolution layer and let us name it as convolution 2. Instead of 32, let us increase it to 64, and we don't want this input, so let me remove it. Done. So after 2 convolution layers, let us flatten out the output of the second convolution layer. Flatten and linear fully connected layers. So model.add flatten, then model.add dense. Here I will reduce from 64 to 32 and activation as ReLU, since it is a hidden layer. And this is the final layer, output layer. Here I will change the number of features, that is number of units, number of neurons to 6, because total number of classes is 6. So I'll be keeping output layer units as 6, and activation will be softmax because ours is a multi-class classification problem. So this is the end of building the model. Next, let us compile the model. Model.compile. Here we given what optimizer and loss we are going to use, and also the metrics. Optimizer equal to Adam. We are going to use Adam optimizer because it helps us with 3 things. One is we don't have to define learning rate. Second is we don't have to deal with the problem of exploding gradients, and third is we don't have to deal with the problem of vanishing gradients. So Adam optimizer makes use of all these 3 issues. Then loss will be categorical cross entropy. Categorical cross entropy. Okay, I was just checking whether I have entered the spelling correct. And then metrics as accuracy, because we will be noting down the accuracy. And the metrics, train metrics, I'll be saving the metrics of training in this particular variable. So here model, before that, let me just add one more code block over here. So we have to define steps. So train steps, that is length of train loader, and this is let me comment it out. This is equivalent to total images, total train images divided by batch size, and round it off. So we get it in integer format. Similarly, train step, similarly test loader, total test images, because you have to pass in the number of steps in the epoch. while we are telling the model, while we are training the model. So model dot fit generator, and here we have to pass in the generator, which is our train loader. Then steps per epoch, as I mentioned the number of steps just before this particular code block. For this will be the train steps. Then epochs, let us train for 10 epochs, and then validation data will be test loader, and validation steps will be test steps. So let me just note it down what all we need. First is generator, second is steps per epoch, third is epochs, fourth is validation data. So for some purpose, for some reason it did not copy it. I guess I messed up my clicking. Validation steps. Okay, done. So generator will be train loader, steps per epoch will be train steps, then epochs, let us train for 10 epochs, then validation data, or let us train for 20 epochs. Validation data will be test loader, and then validation steps will be test steps. That's it. So let me put this for training. So it has started to train. So I'm going to pause the video for here, and I'll unpause it when the 20 epochs, when the model gets trained over 20 epochs, just to save the time. Okay, so welcome back, guys. So we are on our 20th of epoch. So far for 19th epoch, the accuracy was 87, train accuracy, and validation accuracy was 74. So there seems to be quite a bit of overfitting. Let's see at the end of 20th of epoch. You can reduce the overfitting by increasing the number of dropout layers. Okay, so validation accuracy, it is 81.77, so almost near to 82%. So now the training and evaluation part is done. So let me just add one more text. So let me type it over here. Model metrics. So we have saved our model metrics in this train metrics, the training metrics. It is basically a dictionary dot history. This history part is the dictionary, train metrics dot history. So first part is loss. First part is training. Sorry, my bad. First part is accuracy, which is the train accuracy. Second part is train loss. Third part is validation accuracy, and fourth part is validation loss. So let me just quickly create 4 different lists based upon these 4 values. So train loss, this will be train accuracy, then this will be, just remove this. This will be test loss and test accuracy. And here I will pass in the key values. So first one will be, so this should be loss. Second will be accuracy. Third will be val loss, and fourth will be val accuracy. Now let us plot for loss, train loss versus validation loss. So plt dot plot in range 20 because we have trained over 20 box. So first one will be train loss and level train loss. Second will be test loss. Test is nothing but validation. So test loss, and then plt dot legend and plt dot x level epochs and plt dot y level loss. Okay, so blue one is the train loss, yellow one is the validation or test loss. Similarly, let us plot for train accuracy versus validation accuracy. Since I have written validation, let me just convert it to validation so the consistency is maintained. Then in code block, I'll copy paste it. Instead of train loss and test loss, it should be accuracy. And similarly, accuracy, and this loss should be accuracy. Let me plot. So blue one is the test accuracy, and the fluctuating yellow one is the test accuracy. Blue one is train and yellow one is test or validation accuracy. Now model metrics is done. Now let us move on to model performance. Performance demonstration. For this, let me quickly create list of images which are in this seg_pred folder. So pred list. So that will be seg_pred slash seg_pred and the file name. Let me quickly convert this to f string for I in os.list directory, and here I'll pass this seg_pred. Done. For demonstration purpose, I'll display this list. So here we have got the path of the images which are in this seg_pred. Now coming on to the next line of code. So first we will read the image using the pillow library. Then we will convert that image to numpy array. Then we will add one more dimension to that particular numpy array, because while training the model, we have added the dimension of batch number. My bad, sorry. We have added the dimension of batch size to it. So just one image will consist of 3 dimensions: height, width, and the input, the color channel, whether it is 1 or 3. Since ours is a color image, it will have 3. It is a 3 input channel image. So it will be a 3-dimension image. So we will have to add a 4th dimension. So let us proceed. So img equal to image dot open, and for display purpose, let us select the 10th image from this spread list. 10, and let us reshape this particular image as per our image data generator. So in image data generator, if you see, we have selected target size as 128 by 128. Height and width, we have to change it to 128 by 128. So image dot resize 128 by 128. You have to pass in a tuple in this resize function. So display image. So we will get to see what sort of image it is. Then we will convert this image to array. Np dot array image. Once we got this, we will convert this to a 4-dimension array. So image array dot np dot new axis. Once we got this, we will pass this through our image generator. So whatever standardization we have entered in image generator, which we have used to train our model, so the same standardization will be applied to this image gen img. So we have to pass in through into the standardized function. And once it is done, then we will pass this image array to our model. So the output of the model will be in terms of probability for the 6 classes. We will select that class which has the highest probability. So probability will be model, and then we will pass image array as the input. It should be img image array. And then we will select that index which holds the highest value, which holds the highest probability. So prediction equal to numpy dot argmax. This will select the this will return the index which has the highest probability value. Probability. And then we will print idx. We have already created this dictionary where key values are from 0 to 5, 0, 1, 2, 3, 4, 5, and keys are 0, 1, 2, 3, 4, 5, and values are building, sea, road, street, mountain, glacier. So let us pass the key value, which is the prediction, and let us see. So I think we have to convert this image to float first. img array equal to img as type float. Yeah, so now if you see, it is correctly predicting this as forest. So let me just put it over here for our more understanding. Model prediction. Model prediction as float. So as forest, my bad. So let me put the marker below this print. And now let us just loop over this. Let's take loop over for 10 images. Let's see the prediction for I in range 10. And now we will use the random library number equal to randint. Randint will take first parameter, we will start it from 0, and last number will be the length of this prediction list. So it will return a number between 0 and whatever the contents, how many images this spread list contains. So it will randomly generate an integer and give it to us, and that we will pass it over here in this prediction list. So it will randomly select a path and feed it to the image.open function. So let us see. So first one, we have got mountain. This image does look like a mountain. Second one, model has predicted as forest. This looks like a forest. This one, this white, I guess it is snow, and hence it has classified it as glacier. Here again we see snow, so glacier. Here we see skyscraper, so buildings. Then here we are seeing mountains, so it has predicted as mountain. So 10 images it has correctly classified. So the performance of the model that we have trained seems to be quite robust. So because we have received 81.77, so that is almost 82% accuracy. So that's it for building your own CNN model using Tensorflow Keras. That's all for this video. If you have any queries, or if you want to collaborate with me for Python or data science or machine learning, you can drop me a mail on shaunak.python@gmail.com. The same is mentioned in the description. And if you want to refer this particular notebook, it will be hosted on GitHub. So the link of the GitHub will be posted in the description of this video. For more such videos regarding machine learning, deep learning, and data science, along with some other videos related to movies, games, and footballs, you can subscribe to my channel. Thank you. Bye and stay safe.